The universe is far stranger than it looks. Behind the stars and galaxies is a hidden structure built on distance, darkness, and forces we still cannot fully explain. That emptiness may be the reason life became possible, but it may also be the same force leading everything toward a colder, lonelier future. And today, we explore why the universe is empty for a reason, and why that truth is terrifying. Now, let's find out. The night sky looks full. That's the lie. Step outside on a clear night, far from any city, tilt your head back, and your brain instantly registers crowded stars layered over stars, the faint smear of the Milky Way arcing overhead, light arriving from every direction at once. It feels like evidence that the universe is teeming, dense, overflowing with matter. That feeling is one of the most convincing optical illusions in human experience. Your eyes are collecting photons from objects separated by trillions upon trillions of miles and flattening everything onto a single two-dimensional surface above you. Distance disappears. The gaps disappear. What remains is only the light, stitched together into something that looks, to every human brain that has ever existed, like fullness. It is not fullness. It is the farthest thing from it. To understand what the night sky is actually showing you, you need a comparison that forces the real scale into your body, not just your head. So, here it is. Shrink the sun, our sun, wide enough to fit 1,300,000 Earths inside it, down to the size of an orange. A regular orange, the kind you'd peel at breakfast. Place it on a table. At that scale, Earth becomes a grain of sand sitting about 41 feet away. Fine. 41 feet is something you can pace out in a parking lot. That part still feels manageable. Now find Proxima Centauri, the nearest star to our solar system, the absolute closest one. In reality, it sits 4.24 light-years away. And in our orange scale model, that same star would be another orange placed approximately 2,600 miles from the first. 2,600 miles. That is the distance from New York City to Los Angeles, and then keep going. Another 600 miles west out over the Pacific Ocean before you place the second orange down. 2 oranges, one on the East Coast, one somewhere past California, floating over open water. And between those 2 oranges, between our sun and its nearest neighbor, at a scale where the entire sun fits in your hand, there is nothing. Not thin air, not floating particles, not some faint interstellar haze you could theoretically detect with the right instrument. Virtually nothing. A vacuum so complete that the best laboratory vacuum humans have ever engineered would seem crowded by comparison. Pure, cold, unbroken emptiness stretching across the equivalent of a cross-continental distance. That is what neighboring stars means in space. That is the reality hiding behind every pinpoint of light in the night sky. Now take that emptiness and multiply it across the entire galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. 400 billion suns, each separated from the others by distances of that same crushing, empty scale. If you counted 1 star per second without stopping, you would still be counting more than 12,000 years from now. The galaxy sounds, on paper, like it should be packed like matter stacked on matter. Impossible to cross without running into something. Do the actual math, though. Calculate the combined volume of every single star in the Milky Way, all 400 billion of them added together, and compare it against the total volume of the galaxy itself. The result? Stars fill less than 1/10,000,000th of 1% of the Milky Way's total volume. Written plainly, the Milky Way is more than 99.9999% empty space. All the fire, all the nuclear fusion, all the gravity and light and motion, everything we associate with the galaxy's existence, amounts to a rounding error against the surrounding nothing. This is not metaphor. This is the measured, calculated reality of the place we call home. Before we go any further, here is a question worth pausing on. What percentage of the total universe do you think visible matter makes up? Not just stars, but everything detectable, all planets, all gas clouds, all dust, every atom of every element across every galaxy ever observed. Take a real guess right now. Hold that number in your head. We will come back to it, and I will tell you this much in advance: whatever you guessed, it is almost certainly too high, probably by more than you are comfortable with. There is something genuinely disorienting about sitting with this reality. Humans have spent tens of thousands of years reading the night sky and building their entire sense of cosmic scale from what they saw. The stars looked numerous. Space looked populated. The universe, by every visual impression available to our eyes, looks like a place full of things. It is not full of things. It is almost entirely made of nothing, with a thin, barely there scattering of matter suspended in the dark. And yet we call ourselves citizens of the universe. It shows up on coffee mugs, on posters, in planetarium speeches delivered with great feeling. Technically true, sure. But consider what that citizenship looks like in literal physical terms. We are living inside a structure that is 99.999% empty space. On a planet, 9% empty space. On a planet that at orange scale shrinks to a grain of sand 41 feet from a piece of fruit. Proudly claiming membership in a cosmos whose primary ingredient is vacuum. That is a remarkable level of confidence for a species occupying 0.0001% of the available floor plan. The audacity, honestly, is impressive. But the distances between stars are only the opening the moment you step outside the galaxy. The numbers will not let you sleep. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2,537,000 light-years away from us. That number deserves a real moment, not to admire it abstractly, but to feel what it actually means. The light reaching your eye from Andromeda tonight left that galaxy 2,537,000 years ago. At that moment, anatomically modern humans barely existed. No cities, no agriculture, no written language, no concept of a galaxy, a universe, or science itself. Every human civilization ever recorded: Mesopotamia, Egypt, Greece, Rome, the Renaissance. Every war ever fought and every idea ever written down fits inside a tiny sliver of the time that light has been crossing empty space to reach you. It just now arrived from our nearest large neighbor. On a clear night, you can see it with the naked eye, a faint smudge in the constellation Andromeda, and have absolutely no felt sense of the abyss behind it. Here is the comparison that makes the distance impossible to dismiss. Compress the entire Milky Way, 100,000 light-years across, down to the size of a quarter. One coin, place it on a table in New York City. At that exact same scale, Andromeda becomes another quarter sitting in Philadelphia, approximately 95 miles away. Two coins, two cities, one gap between them. But between those two coins, across every single inch of those 95 miles, there is nothing, no air, no floor, no medium of any kind, complete vacuum. Two tiny disks of compressed galaxy, each holding hundreds of billions of stars, separated entirely by emptiness. That is what neighboring galaxies look like when the actual distances are taken seriously rather than compressed into a tidy diagram. Here is a question to sit with right now. If you could travel at the speed of light, 670 million miles per hour, the absolute speed limit of the universe, how long would it take just to escape the Milky Way? Not reach Andromeda? Not cross to any other galaxy? Simply get from one edge of our own galaxy to the other. 100,000 years. traveling at the speed of light, without a single stop, for 100,000 years. That is what crossing the Milky Way takes. Light that can circle the entire Earth 7 times in 1 second needs 100,000 years to traverse our galaxy from edge to edge. Andromeda is 25 times farther than that. 25 times farther than a journey that already requires 100,000 years at the fastest speed anything in the universe can travel. Now zoom out 1 level further, because the Milky Way and Andromeda are not floating alone. They belong to a broader structure called the Local Group, a gravitationally bound collection of approximately 80 galaxies, all held together by mutual gravity, slowly orbiting a shared center of mass. 80 galaxies in one region of space. That sounds, on paper, like a crowd, like genuine company. The Local Group spans a bubble roughly 10 million light-years in diameter. 80 galaxies spread across 10 million light-years. Picture taking 80 grains of sand and scattering them randomly across the entire continental United States. Every grain of sand is a galaxy. Every square inch of land between them is pure vacuum. That is the actual population density of the Local Group. And this collection, already so sparse that the human mind struggles to hold it, is still described by astronomers as a relatively dense region of space. Outside it, the voids begin. Regions stretching hundreds of millions of light-years in every direction where there are no galaxies at all. No lone stars drifting in the gap, no thin gas clouds, nothing, just cold, expanding space with no contents and no horizon. The Local Group is not a hub. It is a small island, and the ocean around it goes on longer than any comparison can carry. People in dense cities sometimes feel suffocated. Too many neighbors. Not enough breathing room. Nowhere to go that isn't already full of someone else. Cosmically speaking, we live in one of the most gravitationally concentrated regions of the known universe, inside a supercluster, inside a galaxy group, inside a galaxy. And our nearest large neighbor still required 2,537,000 years of light travel for its glow to reach us. If the universe posted an honest listing for our cosmic address, it would read deep rural, extreme isolation, nearest comparable neighbor, 2.5 million light-years out. Surrounding area expanding further away every single second. No amenities for hundreds of millions of light-years in any direction. We have genuinely no frame of reference for what isolated means. But if galaxies are already this sparse, what does the larger structure of the universe actually look like? The answer will completely change the way you imagine space. The Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, DES. I spent years doing something no human civilization had ever attempted at this scale, building a true 3-dimensional map of the universe, cataloging the positions of tens of millions of galaxies spread across hundreds of millions of light-years in every direction. The project took decades of telescope time, petabytes of data, and the coordinated effort of hundreds of scientists across multiple continents. When those maps finally rendered into something a human could look at, the image on screen stopped people cold. Not because it was chaotic, not because it was random, because it was structured. Eerily, intricately, almost impossibly structured, like something had been deliberately arranged by a hand operating at a scale beyond all comprehension. The universe looks like a spider web. Long filaments of galaxies stretch across hundreds of millions of light-years, threading between massive nodes where galaxy clusters pile up at the intersections, like dew collecting at the knots of a web. Flat sheets of matter curve around enormous empty regions, and nested inside those empty regions, sitting at the center of them. Surrounded by the filaments on all sides are the voids, spherical bubbles of space, vast beyond anything the human mind was built to process, almost completely devoid of galaxies. These structures have a name: cosmic voids, not metaphorical emptiness, not a poetic description. Measured, mapped, confirmed regions of space where the universe simply decided not to put anything. One of the largest known voids sits in the direction of the constellation Bodas. The Bodas void, sometimes called the Great Nothing, spans approximately 330 million light-years in diameter. To put that in context, the entire distance from the Milky Way to Andromeda, the gap we spent all of Part 2 establishing as almost incomprehensibly large, is 2,537,000 light-years. The Bodas void is more than 130 times wider than that distance. It is not a gap between two things. It is an absence so enormous it dwarfs the structures surrounding it. When astronomers first measured it in 1981, the finding caused genuine controversy. A void that size conflicted with prevailing models of how matter was supposed to distribute itself after the Big Bang. Several astronomers publicly questioned whether the measurement could be correct. Papers were written, the data was reanalyzed, and the Bodas void held. 330 million light-years of space, and almost nothing inside it. A small number of galaxies have since been found near its edges, 60 or so, clinging to the boundary, but the interior is as close to true, absolute emptiness as anything in the observable universe. Now make it personal. If the Milky Way were somehow relocated to the exact center of the Bodas void, if our entire galaxy, with all its 400 billion stars, were dropped into the middle of that great nothing, the nearest galaxy outside our own would be so far away that its light, traveling at 670 million miles per hour without stopping, would not have reached us yet in the entire current age of the universe. 13.8 billion years of continuous travel at the maximum speed anything can move, and the light still would not have arrived. Every direction you looked, you would see only our own galaxy hanging in absolute darkness, no other light, no other structure, nothing on the horizon in any direction, for longer than time has existed so far. That is one void. The observable universe contains millions of them. Here is the number that reframes everything you thought you knew about where matter lives. Cosmic voids occupy approximately 80% of the total observable volume of the universe. 80%. All the filaments, all the sheets, all the galaxy clusters, every luminous structure visible in every map astronomers have ever produced. All of it exists within the remaining 20% of the volume. And within that 20%, most of the space is still empty space between individual galaxies. The actual matter stars, gas, dust, everything that has ever been cataloged is compressed into a vanishingly small fraction of the total volume available. The universe is not a place where matter exists with some empty space between it. It is empty space, structured and vast, with thin threads of matter stretched carefully across the surfaces of enormous nothingness, like frost forming on the inside of a dark window. Here is the question worth sitting with right now. If 80% of the universe is completely void, if the dominant feature of cosmic structure is absence rather than presence, what is holding the other 20% together? What keeps the filaments from dissolving, the galaxy clusters from scattering, the entire web from collapsing into uniform emptiness? The gravity produced by all the visible matter in the universe is not sufficient. The math has been done many times by many different groups of scientists, and it does not close. Something else is holding the structure in place. Something distributed through the cosmos in quantities far exceeding everything we can see. Something providing gravitational scaffolding to the entire web without ever appearing in a photograph. The universe is basically one giant block of Swiss cheese, except the cheese only makes up 20% of the total volume, and everything else is holes. And somehow, against all intuition, the cheese knows exactly where to arrange itself. held precisely in place by something the cheese itself cannot see or touch or measure directly. And this is what makes it truly strange. Those voids are not actually empty. There is something there, something we cannot see, cannot touch, but whose gravitational pull we can feel. In 1933, a Swiss astronomer named Fritz Zwicky pointed his telescope at the Coma Cluster, a dense, rich collection of galaxies sitting roughly 320 million light-years away, and set about measuring how fast the individual galaxies inside it were moving relative to one another. It was methodical work, careful work, the kind of measurement that was supposed to confirm what physics already predicted. What he found instead made no sense at all. The galaxies were orbiting the cluster's center at velocities so extreme that the gravity produced by all their combined visible mass, every star, every cloud of gas, every piece of detectable matter in the entire cluster, added together, should not have been anywhere near sufficient to hold them. By every calculation available to physics in 1933, those galaxies were moving far too fast for the cluster to remain intact. They should have flung themselves apart long ago, scattering into the surrounding intergalactic space millions of years before Zwicky ever aimed a telescope at them. They had not scattered. They were right there, perfectly bound, orbiting as though held by a gravitational grip 5 to 10 times stronger than visible matter alone could generate. Something was holding them, something with enormous mass that produced no detectable light, no radio waves, no X-rays, no signal of any kind that Zwicky's instruments could pick up. He called it Dunkle Materie, dark matter, and for decades, the idea sat at the uncomfortable margins of mainstream science acknowledged. Troubling, but not yet taken seriously enough to transform the field. Then came Vera Rubin. In the 1970s, working with astronomer Kent Ford, Rubin measured the rotation curves of spiral galaxies with exceptional precision, plotting how fast stars at different distances from a galaxy's center were orbiting around it. The physics was well established. The same gravitational logic governing our solar system predicted a clear result. Stars at the outer edges of a galaxy, far from the concentrated mass at the center, should orbit more slowly, just as Neptune moves far more slowly than Mercury in its path around the Sun. The outer stars should be moving lazily. The rotation curve should drop. It did not drop. Across galaxy after galaxy after galaxy, the curve stayed flat. Stars at the outermost edges were orbiting just as fast as stars near the bright, dense center, sometimes faster. The visible matter, all those billions of stars making up the luminous disk, was not generating nearly enough gravity to explain what Rubin was measuring. There had to be more mass, invisible mass, distributed in a vast spherical halo extending far beyond the visible boundaries of each galaxy, contributing gravitational pull without contributing a single photon of detectable light. Zwicky had been right, and Rubin's work, replicated across hundreds of different galaxies over the following years, made dark matter impossible to dismiss any longer. Dark matter does not emit light. It does not reflect light. It does not absorb light in any wavelength visible: infrared, ultraviolet, X-ray, radio, none of it. It passes through ordinary matter with almost no interaction whatsoever. The protons, neutrons, and electrons that make up every atom of everything you have ever seen are essentially transparent to whatever dark matter is. Right now, if current models are correct, an enormous flux of dark matter particles is streaming through the walls of the building around you, through the floor, through your body, through the chair, through the earth itself, leaving no trace, triggering no detector, depositing no energy. It moves through the physical world we inhabit as though the physical world barely exists, and yet it has mass, real, measurable by consequence mass, mass that curves space-time exactly as Einstein's equations predict, pulling on everything around it with genuine gravitational force. bending the paths of objects and light alike. Which brings us to gravitational lensing, the most powerful indirect evidence for dark matter's existence. When light from a distant galaxy travels toward us and passes near a massive object along the way, that mass bends the light's path, distorting the image of whatever lies behind it. Astronomers can calculate precisely how much bending a given amount of visible mass should produce, and repeatedly, in cluster after cluster, the observed bending is far greater than the visible mass can explain. The light is being deflected by something with enormous gravitational presence and no detectable physical form. Maps of where the lensing originates point consistently to regions of space containing little or no visible matter. That invisible deflection, that warping of light by something that casts no shadow and emits no glow, is the clearest signature dark matter leaves on the observable universe. So if dark matter is invisible and does not interact with light, how do we know it exists? Every independent line of evidence converges on the same answer: galaxy rotation curves, gravitational lensing, the dynamics of galaxy clusters, the structure of the cosmic web itself. None of it works without dark matter in the equations. Remove it, and galaxies fly apart. Remove it, and the filaments never form. Remove it, and the universe we observe cannot exist. Now here is the number that should permanently alter the way you see the cosmos. Dark matter makes up approximately 27% of the total mass energy content of the universe. All ordinary matter, every element on the periodic table, every star ever catalogued, every planet ever found, every ocean and mountain and living thing and human thought and human civilization that has ever existed anywhere makes up approximately 5%. Dark matter outweighs all of that by a factor of roughly 5 to 1. Everything on the periodic table, every star ever named, every world ever discovered, every atom of everything anyone has ever seen or touched or built or loved it, is the universe's footnote, 5%. We have spent our entire scientific history studying that 5% and calling it the cosmos, the whole thing, the sum of reality. We were reading the margin notes and mistaking them for the book. But if dark matter is already this strange, if an invisible substance that outweighs everything we can see by 5 to 1 is still only 27% of the universe, then brace yourself for what fills the remaining 68%. Because whatever it is not pulling things together. It is doing the exact opposite, and it is winning. In 1998, 2 independent research teams set out to do something straightforward: measure how fast the universe was expanding and calculate how much it was slowing down. The slowing down part was the assumption, not a guess, a reasonable physics-backed expectation. The universe has been expanding since the Big Bang, and gravity, the great decelerator, should be pulling all that matter back together, gradually putting the brakes on the expansion. The question the teams wanted to answer was simply how strong those brakes were. Were they strong enough to eventually reverse the expansion entirely? Or would the universe coast outward forever, slowing but never quite stopping? To answer that, both teams used a specific type of exploding star called a Type 1a supernova as their measuring tool. These explosions are remarkably consistent. They always detonate with almost exactly the same peak brightness, which makes them reliable distance markers across cosmic scales. Measure how bright one appears from Earth, compare it to how bright it actually is, and you can calculate precisely how far away it sits. Do that for supernovae at different distances, and you can reconstruct the expansion history of the universe across billions of years. Saul Perlmutter led one team, Brian Schmidt and Adam Rees led the other. They worked independently, using different telescopes, different data sets, different analysis pipelines. When both teams finished their calculations in 1998, They compared results. The universe was not slowing down. It was speeding up. The distant supernovae were dimmer than they should have been if expansion were decelerating, meaning they were farther away than expected, meaning the universe had been expanding faster than anticipated and was continuing to accelerate. Both independent teams, working separately, arrived at the same impossible-seeming conclusion. Something was pushing space apart, not just maintaining the expansion, but actively accelerating it. Something with repulsive force acting against gravity on the largest scales, driving galaxies away from each other faster with every passing moment. That something was named dark energy, and it earned Perlmutter, Schmidt, and Reese the Nobel Prize in Physics in 2011. Dark energy is unlike anything else in the known universe. It does not concentrate in any particular location. It does not gather around massive objects the way gravity does. It does not thin out in empty space the way light dims with distance. It is distributed with perfect uniformity across all of space. Every cubic centimeter of the universe contains the same density of dark energy as every other cubic centimeter. The room you are sitting in right now contains dark energy. The empty space between galaxies contains it. The interior of the Oert's void contains it, everywhere, in equal measure, with no variation and no preference for any location over any other. And it makes up approximately 68% of the total energy content of the universe. To be clear about what that means alongside what we established in Part 4, dark matter is 27%, ordinary matter is 5%, and dark energy is 68%. Everything we have ever seen, touched, measured, or built sits in that 5%. The invisible gravitational scaffold of dark matter sits in the 27%. And dark energy, this uniformly distributed, location-indifferent, repulsive force that is actively accelerating the expansion of all space, owns the remaining 68%. Dark energy is not a minor player in the cosmic budget. It is the dominant feature of the universe's energy content, and we have essentially no idea what it fundamentally is. What dark energy does, in physical terms, is this: it stretches space itself, not the objects within space, the space between them. Right now, as you read this, the fabric of space between galaxy clusters is being pulled wider, creating more distance between them with every passing second. Galaxies are not flying outward through space like shrapnel from an explosion. Space itself is expanding, generating new distance out of nothing. And it is doing so faster today than it did yesterday. And it will do so faster tomorrow than it does today. Here is the question that trips almost everyone up. If space is expanding everywhere, if dark energy is distributed through all of space, including inside our solar system, inside the Milky Way, inside the room you are in, why are we not being stretched? Why is the Earth not expanding? Why is the Milky Way not being pulled apart? The answer is that dark energy's repulsive effect is extraordinarily weak at small scales. Gravity, electromagnetism, and the nuclear forces that hold atoms, planets, stars, and galaxies together are locally far stronger than dark energy's push. Dark energy only wins at the very largest scales between galaxy clusters, separated by hundreds of millions of light years, where no other force is strong enough to maintain a gravitational bond. At those scales, dark energy dominates. Below those scales, the other forces hold everything together without difficulty. The Earth stays intact, the solar system stays bound, the Milky Way stays coherent. But anything not gravitationally tethered to something local is being carried away, and the carrying is accelerating. Dark energy is the only thing in the universe that gets more powerful as space expands. More space means more total dark energy, which drives more expansion, which creates more space, which generates more dark energy. It is a feedback loop written into the architecture of the cosmos, self-reinforcing and unstoppable by any mechanism currently known to physics. Honestly, as business models go generating your own fuel from the empty space you create, it is the most perfect self-sustaining operation ever conceived. Every other force in the universe runs down eventually. Dark energy just keeps compounding. The universe is expanding faster every single day. And that acceleration is not a temporary phase, not a cosmic hiccup, not something that will eventually balance out. It is the direction the universe is heading toward. More space, more separation, more emptiness, at a pace that will only increase. What that means for galaxies, for stars, for everything we can currently see in the night sky, and what it ultimately means for us is a story that goes to places most people would prefer not to look at directly. The universe is expanding faster every single day. What that means for everything inside it, including us, is a question that goes somewhere most people would rather not follow. But that is exactly where we are going next. According to the Planck satellite's 2018 data release, the most precise measurement of the universe's composition ever produced, the cosmos breaks down like this: 5% ordinary matter, 27% dark matter, 68% dark energy, 5%. That is the ordinary matter slice. Every atom of hydrogen, helium, carbon, oxygen, iron, and every other element on the periodic table. Every star that has ever burned in the history of the universe, every planet that has ever formed around any star anywhere, every ocean, every mountain range, every living cell, every thought ever generated by a biological brain anywhere in the cosmos, every black hole ever measured, every nebula ever photographed, every galaxy ever catalogued across every survey ever conducted by every telescope humans have ever built. All of it, the complete, total sum of everything science has ever directly observed, studied, touched, described, or even theorized about from direct evidence, sits inside that 5%. The other 95% remains, in the most honest and uncomfortable sense of the word, unknown. Think about what that actually means for the entire enterprise of human knowledge. Everything physics has built over 4 centuries: quantum mechanics, general relativity, the standard model of particle physics, the complete periodic table of elements, every equation ever written on every blackboard, in every university, on every continent. All of it was constructed entirely from interactions with 5% of what exists in the universe. We built our complete model of physical reality from a sample size of 5%, spent centuries refining it, taught it to generations of students, and then looked up at the remaining 95% hovering above us and admitted we do not know what that is. We cannot see it, cannot touch it, cannot detect it directly, and cannot yet explain it from first principles. Here is the comparison that makes this impossible to rationalize away. Imagine sitting down with a 1,000-page novel. You read it carefully from beginning to end, following every character arc, every plot development, every line of dialogue, every scene. You reach the final page, close the book, and feel genuinely confident that you understand the story, the themes, the structure, the meaning. Then someone informs you that 950 of those pages were printed in invisible ink. You read 50 pages. The other 950 were there the entire time, bound inside the same cover, part of the same narrative, and you never saw a single word of them. That is the epistemological position science currently occupies with respect to the universe. We have read 50 pages with extraordinary care and precision, written detailed analyses of the characters, and called it an understanding of the book. The search for what fills those missing pages specifically, what dark matter actually is at the particle level, has been one of the most sustained, expensive, and humbling hunts in the history of physics. The leading candidates each have names and theoretical pedigrees, Weakly interacting massive particles, known as WIMPs, were for decades the front-runner hypothetical particles predicted by supersymmetry theory, heavy enough to account for dark matter's gravitational effects, interacting with ordinary matter, weakly enough to explain their invisibility, and theoretically detectable under the right experimental conditions. Axions are another candidate, originally proposed in the 1970s, not to explain dark matter, but to solve a separate problem in particle physics called the strong CP problem. They turned out to have properties that would make them excellent dark matter candidates as well. Sterile neutrinos represent a third possibility, heavier, more reclusive cousins of the nearly massless neutrinos, already confirmed to exist, interacting even more weakly with ordinary matter than regular neutrinos do. Each of these candidates has been searched for with increasing technological sophistication across decades of dedicated experimental effort. As of 2025, not one of them has been directly detected. The search has not been half-hearted. The LAX Zeppelin detector, known as LZ, sits approximately 1.5 miles underground inside the Sanford Underground Research Facility in the Black Hills of South Dakota. The depth is deliberate that much rock above the detector filters out the overwhelming majority of cosmic ray particles that would otherwise bombard the instrument constantly and make any dark matter signal impossible to distinguish from background noise. Inside the facility, the detector's core contains 10 metric tons of liquid xenon, chilled to temperatures just a few degrees above absolute zero, surrounded by layers of shielding and monitored by hundreds of photomultiplier tubes, waiting for the faint flash of light that a dark matter particle collision with a xenon nucleus would theoretically produce. The engineering required to achieve and maintain those conditions, deep underground, for years at a time, represents a genuinely remarkable technological achievement. XENOMAE operates on the same principle inside the Gran Sasso Mountain in central Italy, with its own multi-ton xenon target and its own international collaboration of physicists. Both experiments represent hundreds of millions of dollars of investment, decades of development, and the dedicated careers of hundreds of scientists. Both are working exactly as designed, achieving the sensitivity levels they were built to achieve. Dark matter has not produced a single confirmed signal in either of them. Every year, these detectors run without a detection. They do not disprove dark matter's existence. The gravitational evidence for it remains overwhelming and completely unchanged. What the silence does is progressively eliminate the regions of theoretical space where WIMPs could plausibly hide. The sensitivity of these detectors now rules out enormous swaths of the parameter space where WIMP dark matter was predicted to sit. Either dark matter is something other than a WIMP entirely, or it is a WIMP that interacts with ordinary matter so weakly that catching it may require instruments we do not yet know how to build. The hunt has not failed, but it has forced a serious reckoning with whether the most popular theoretical candidates were ever correct. Here is something worth thinking about right now. If dark matter genuinely passes through ordinary matter with almost no interaction, if it streams through solid rock, through the Earth's mantle, through oceans and continents and everything on them, without slowing down, then right now, as you sit wherever you are, an enormous flux of dark matter is almost certainly moving through your body, through your chest and your skull and your hands. Estimates suggest something on the order of hundreds of millions of dark matter particles passing through every square inch of your body every single second, touching nothing, depositing no energy, leaving no trace whatsoever, completely indifferent to the fact that you are there. You are not solid to dark matter. To dark matter, you are barely a suggestion. We have carved tunnels 1.5 miles into the Earth, built instruments of extraordinary delicacy, cooled them to temperatures colder than anything in the natural solar system, and sat in near-perfect silence for years, waiting. Dark matter has not acknowledged the effort in any detectable way. As first dates go, This one is historic in its one-sidedness. We planned everything, arrived early, set the table carefully, and dark matter has not shown up, sent a message, or given any indication it is aware this relationship exists. The most abundant form of matter in the universe is, from an experimental standpoint, the most indifferent thing science has ever tried to court. But if we do not know what dark matter is, we know even less about dark energy, and that ignorance may change every prediction we have ever made about what comes next. Einstein added the cosmological constant to his field equations of general relativity in 1917, and his reasoning was straightforward. The universe was supposed to be static. Stars existed. Galaxies existed. Everything appeared to occupy fixed positions in space. But Einstein's equations, left unmodified, predicted that a universe containing matter could not hold still. Gravity would inexorably pull everything inward until the whole thing collapsed. To prevent that collapse from appearing in his mathematics, Einstein introduced an additional term, represented by the Greek letter lambda, a kind of uniform repulsive energy built into the fabric of space itself, finely tuned to exactly balance gravity and hold everything in equilibrium. It worked. Mathematically, the static universe held. Then, in 1929, Edwin Hubble published the observations that changed everything. Galaxies in every direction were moving away from us, with more distant ones receding faster. The universe was not static. It had never been static. It had been expanding since the beginning, and no balancing term was needed or appropriate. Einstein reportedly called the cosmological constant the biggest blunder of his scientific life, struck it from his equations, and the field moved on without it. The irony is almost architectural in its perfection. In 1998, when the supernova teams discovered that the expansion of the universe was not decelerating, but accelerating, cosmologists reached back into the theoretical discard pile and retrieved lambda, dark energy. The force responsible for that acceleration behaves in a way that is mathematically nearly identical to Einstein's cosmological constant. It is distributed uniformly through all of space. It does not thin out as space expands. Its energy density remains constant even as the volume of the universe grows, which means the total amount of dark energy increases as space increases, which drives more expansion, which creates more space. Einstein removed the right term for the wrong reason and spent the last 2 decades of his life unaware that the universe had been running on it the whole time. But here is where the situation becomes genuinely and consequentially unsettled. The cosmological constant interpretation of dark energy assumes that lambda is exactly that constant, unchanging through time. The same value it had 13.8 billion years ago that it has today and will have infinitely into the future. That assumption sits at the foundation of the standard cosmological model, lambda CDM, which has organized and successfully described the large-scale structure and evolution of the universe for a generation of physicists. That assumption is now under serious pressure from 2 directions simultaneously. The first is what physicists call the Hubble tension. There are 2 primary methods for measuring the universe's current rate of expansion. A value called the Hubble constant, H0. The first method works backward from the early universe using precise measurements of the cosmic microwave background, the faint thermal glow left over from 380,000 years after the Big Bang. Physicists can calculate what the expansion rate should be today based on the known physics of the early cosmos. The Planck satellite's measurements give a value of approximately 67 kilometers per second per megaparsec. The second method works from the nearby universe directly using Cepheid variable stars and Type 1a supernovae as calibrated distance markers. Astronomers measure the expansion rate as it is right now. In the universe, we can observe locally. That method, anchored by teams like the one behind the SH0ES project, consistently returns approximately 73 kilometers per second per megaparsec, 67 versus 73, a 9% discrepancy. In a scientific field where measurements routinely achieve sub-percent precision, a 9% gap between two well-established, independently verified measurement methods aimed at the same physical quantity is not a calibration issue. It is not measurement error. Both methods have been checked, rechecked, and refined for years, and the gap has not closed. It has, if anything, grown more statistically significant as the data has improved. Something in the standard model is not capturing reality correctly. Physicists do not yet agree on what that something is. The second pressure point arrived in 2024, when the Dark Energy Spectroscopic Instrument published its first major cosmological results, drawn from a survey of over 6 million galaxies spanning approximately 11 billion years of cosmic history. The data carried a suggestion that, if confirmed by further analysis and future surveys, would force a fundamental revision of the standard framework. Dark energy may not be constant. Its strength may have varied over cosmic time, and the variation the data hints at points toward dark energy being stronger in the past and weakening toward the present, or potentially oscillating in ways no current model fully predicts. If dark energy evolves rather than remaining fixed, the cosmological constant is not the right description of it. Lambda CDM needs to be replaced or substantially rebuilt. The equations governing the universe's future change, and the range of possible endings for the cosmos widens considerably. Here is the question that matters. If dark energy is not constant, if its strength can change over time in either direction, what is the worst case? What sits at the dangerous end of the possibility space? If dark energy weakens sufficiently, gravity wins eventually, and the universe recollapses. If dark energy strengthens over time without limit, it eventually overcomes every other force at every scale, not just the gravity between galaxy clusters, but the gravity within individual galaxies, within solar systems, within planets, within molecules, within atoms. Space itself tears apart at every level of structure simultaneously. Nothing holds together. Everything that exists gets shredded down to its most fundamental components, and then those components lose coherence too. Physicists call this the Big Rip, and the 2024 DESI data has not ruled it out. Einstein called lambda the biggest mistake of his life. The universe heard that, kept the idea anyway, and built something far stranger and more dangerous out of it than Einstein ever imagined when he first wrote the term down. The uncertainty about dark energy's true nature is not a theoretical problem. It decides how the universe ends. And there is one specific scenario where nothing survives, not galaxies, not atoms, not space itself. The universe is not randomly distributed. That point deserves to land fully before moving forward. When you look at the large-scale maps produced by the Sloan Digital Sky Survey and DESI, what you are not seeing is matter scattered arbitrarily through space like dust shaken from a cloth. What you are seeing is structure deliberate, repeating, mathematically consistent structure operating across hundreds of millions of light years, filaments stretching like threads between massive nodes, flat sheets of galaxies curving around enormous empty bubbles, voids nested inside larger voids. The whole thing organized into what cosmologists call the cosmic web, and it did not arrive at this arrangement by accident. The origin of that structure traces back to the first fraction of a second. After the Big Bang, during a period called cosmic inflation, a phase of extraordinarily rapid expansion in which the universe ballooned in size by a factor incomprehensibly larger than anything that has happened since. During inflation, the universe was not perfectly smooth. Quantum mechanics, operating at the smallest possible scales, guaranteed tiny fluctuations in energy density regions that were infinitesimally denser than their surroundings, and regions that were infinitesimally less dense. These were not large differences. The variation was on the order of 1 part in 100,000, a smoothness so nearly perfect that describing it as nearly perfect barely does it justice. But inflation took those quantum whispers and stretched them across cosmic scales. What began as subatomic fluctuations became the seeds of large-scale structure slightly over dense regions that would, over billions of years, gravitationally attract more matter, growing denser still, eventually becoming the filaments and nodes of the cosmic web. And the slightly underdense regions became the voids emptied further and further as gravity pulled their matter outward toward the denser surroundings, leaving behind the great bubbles of near-nothingness mapped by modern surveys. The cosmic web is the fossil record of quantum noise from the universe's first moment, written at the largest scales that exist. Dark matter was the architect, long before any star ever formed. Dark matter, already present in enormous quantities and responsive to gravity but invisible to all other forces, began to collapse along the density gradients seeded by inflation. It concentrated first at the intersections of those primordial overdense regions, building up vast invisible halos and filamentary scaffolding across cosmic scales. Ordinary matter, made of protons and neutrons and electrons, followed. Gas fell along the dark matter structure. Channeled by the gravitational wells dark matter had already carved, pooling at the nodes where filaments intersected. There, where gas densities finally became high enough, gravitational collapse produced the first stars. Those stars formed galaxies. Those galaxies clustered along the dark matter filaments like pearls strung along invisible thread, which is, almost exactly, what the maps look like. Without dark matter, none of that sequencing is possible. Ordinary matter alone cannot collapse fast enough. In a universe with only ordinary matter, the pressure from photons in the early universe resists gravitational collapse, preventing the density contrasts from growing sufficiently before the universe expands too much for them to matter. The result would be a universe where matter disperses nearly uniformly across space, never achieving the density required to form stars. No stars means no carbon forged in stellar cores. No carbon means no chemistry of the complexity life requires. No complex chemistry means no biology. No biology means no observers of any kind anywhere. The emptiness of the universe is not a flaw in the design. The voids are not wasted space. The enormous gaps between filaments exist precisely because gravity is efficient. It pulls matter toward the densest regions and leaves behind the regions it has emptied. The cosmic web is what you get when gravity operates on a nearly uniform distribution of matter over 13.8 billion years. The voids are gravity's exhaust. The filaments and nodes are where gravity deposited everything it collected. The structure is the physics, expressed at the largest scale available. Think about that for a moment. If the universe were distributed with perfect uniformity, if every cubic meter of space contained exactly the same density of matter as every other cubic meter, with no variation whatsoever, could life exist? Could anything complex exist? The answer, based on everything physics tells us, is no. A perfectly uniform universe produces no stars, no planets, no chemistry beyond the simplest atoms. Complexity requires contrast. Life requires structure. And structure requires that some regions be denser than others, which means other regions must be emptier. The universe could not have produced us without also producing the voids. They are the same process, the same physics, the same gravitational story told from two different vantage points. The universe spent 13.8 billion years arranging matter into structures complex enough to produce human beings, and humans spent approximately 5 minutes looking up at the sky and complaining that it feels too empty and lonely. The audacity is, again, impressive. The emptiness is not the universe's failure. It is the condition of our existence. The voids are not where life was denied. They are the other side of the coin whose face is every star that ever burned and every world that ever formed. You cannot have one without the other. The universe is empty in exactly the way it needed to be for us to exist. But the way it is changing, the way it is becoming emptier still, faster and faster, with no mechanism to reverse it, that is an entirely different story. The observable universe has a radius of approximately 46.5 billion light-years. That boundary, called the cosmic horizon, or sometimes the Hubble horizon, marks the limit of what we can in principle detect. It is not a wall. It is not a physical edge where space ends. It is simply the distance beyond which light has not had enough time, in the 13.8 billion years since the Big Bang, to travel and reach us. Everything within that sphere is, at least theoretically, visible. Everything beyond it is causally disconnected from us. Information from those regions has not arrived and, depending on the expansion rate, may never arrive. That boundary is not fixed, and it is not expanding in our favor. Because dark energy is accelerating the expansion of space, galaxies sufficiently far away are being carried outward, faster than light can cross the growing distance between us. Their light, already traveling toward us at the maximum speed the universe permits, is losing ground against the expansion of the space it must cross. At a certain distance threshold, the light emitted by a galaxy today will never reach us, not because the galaxy is moving through space faster than light, but because the space between us and that galaxy is being created faster than light can traverse it. Those galaxies are, for all practical and physical purposes, gone, not destroyed, just permanently beyond reach. Right now, approximately 97% of the galaxies within our observable universe are already beyond this threshold, what cosmologists call the cosmic event horizon. They can still be seen, because the light they emitted in the past, when they were closer, is still arriving. But any signal they emit today will never reach us. Any signal we send today will never reach them. The connection is severed, permanently, by the geometry of an accelerating universe. 97%. Of the estimated 2 trillion galaxies in the observable universe, only a small fraction remain within the boundary where two-way communication or travel is physically conceivable. Even in principle, with unlimited technology, the universe is not just large. It is actively becoming less accessible. One galaxy at a time, every second. Project forward approximately 150 billion years. By that point, the accelerating expansion will have pushed the overwhelming majority of galaxies so far beyond the cosmic horizon that they will be invisible, not faded, not dim, but gone from the observable sky entirely. A civilization existing in the Milky Way at that time, looking out with the most powerful telescopes imaginable, would see a universe consisting of a single galaxy, their own surrounded by absolute darkness. No other light sources, no other structures, no evidence whatsoever that the universe contains anything beyond the boundaries of their home galaxy. The cosmic microwave background, the faint thermal glow that tells us today about the Big Bang and the early universe's structure, will have redshifted to wavelengths so long they become undetectable with any conceivable instrument. The information will be gone, not hidden, gone. Think about what that means for a scientist living in that era. Imagine being a brilliant, rigorous, careful astronomer 150 billion years from now, doing exactly what astronomers today do, observing the sky, measuring what exists, building models of the cosmos from available data. Every observation confirms the same picture: one galaxy, surrounded by empty space, with no evidence of any structure beyond it. The natural conclusion, the scientifically justified conclusion from available evidence, would be that the universe contains one galaxy, that conclusion would be wrong by a factor of 2 trillion, and there would be no way to know it. The evidence that would reveal the error: the light from 2 trillion other galaxies will have been carried permanently beyond the horizon by expansion. The universe will have hidden its own history behind a wall of accelerating space. We, right now, are living in what may be the golden era of cosmology. Every generation of telescope has revealed more galaxies, more structure, more history. The James Webb Space Telescope peers back to within a few 100 million years of the Big Bang. The maps from DESI and its successors trace the cosmic web across billions of light years. We have access to a picture of the universe that is genuinely approaching comprehensive, or so it feels. But 150 billion years from now, a civilization with technology far beyond ours will look at a sky that tells them almost nothing, and they will build their cosmology from that impoverished sample, and they will be confident in it. They will be right about everything they can see, and wrong about almost everything that exists. If you are an astronomer living 150 billion years from now, could you figure out that the universe once held hundreds of billions of galaxies? Almost certainly not. The evidence will not exist in any observable form. The history will be written only in the physics of your own galaxy, in subtle signatures that might, with extraordinary cleverness, hint at a larger past. But those hints will be faint, ambiguous, and deeply easy to miss. The universe will look, from that vantage point, like it always contained one island of matter in an infinite dark sea. The astronomers of that era will be, through no fault of their own, the most comprehensively misled scientists in history. And that leads to a question far more uncomfortable than it first appears. If a civilization 150 billion years from now will be missing most of the universe's observable history permanently, irrecoverably, what does that imply about us today, looking back at our own horizon? If we are living in the golden era of cosmology, and future observers will be blind to most of what we can see, then how certain can we be that we are not similarly blind to things that were once visible, but are no longer things that crossed our horizon before our telescopes existed, carrying information we will never recover? And if even we, with every modern instrument available, at what may be the best possible moment in cosmic history to observe the universe, could already be missing pieces that have slipped past our horizon, then the picture we are looking at right now may not be as complete as we assume. The Big Bang model makes precise predictions. One of them concerns ordinary matter, the protons and neutrons that make up atoms, collectively called baryons. Based on the physics of the early universe, specifically the ratios of light elements produced in the first few minutes after the Big Bang and confirmed by measurements of the cosmic microwave background, physicists calculated exactly how many baryons the universe should contain. The number is well established, cross-checked by multiple independent methods, and considered one of the most reliable figures in cosmology. When astronomers went looking for all that matter, counting every star, every gas cloud, every galaxy, everything detectable, they found roughly half of it. The other half was simply not there. Not dark matter, not dark energy. Ordinary matter, protons and neutrons. The stuff we understand completely. The stuff our entire periodic table is built from. The stuff that makes up every object any human being has ever touched. Half of it was missing. This became known as the missing baryon problem, and it sat unresolved for decades, one of the quieter embarrassments in modern cosmology, tucked beside the louder mysteries of dark matter and dark energy. The question was not where the exotic unknown substances had gone. The question was where half of the ordinary, well understood, theoretically fully described matter in the universe had hidden itself. The answer, pieced together through observations spanning from 2017 to 2020, turned out to be the filaments, not inside galaxies, not invisible gas clouds, not in any form that conventional telescopes were designed to detect. The missing baryons were strung along the same cosmic web filaments that define the large-scale structure of the universe, but in a form so diffuse and so hot that it had slipped past decades of observation entirely. Astronomers call it the warm-hot intergalactic medium, or WIM. Gas heated to temperatures between 100,000 and 10 million degrees Kelvin, stretched so thin across the filaments connecting galaxy clusters that its density is almost unimaginably low in some regions, just a few atoms per cubic meter, hot enough to be nearly invisible to optical telescopes, diffuse enough to be nearly invisible to X-ray telescopes, present everywhere along the cosmic web and detectable by almost nothing. The confirmations came from two directions at once. X-ray observatories, including XMM, Newton and Chandra, began detecting faint emission and absorption signatures consistent with YM along lines of sight between galaxy clusters, particularly in a filament connecting the clusters Abell 241 and Abell 2244, reported in 2017. Separately, fast radio bursts. Brief, extraordinarily intense pulses of radio waves originating from distant galaxies provided a completely independent confirmation method. As a fast radio burst travels through intergalactic space, the free electrons it encounters disperse its signal in a measurable way, and the degree of that dispersion encodes information about the total amount of matter the signal passed through. By 2020, analysis of multiple fast radio bursts had confirmed that the dispersion measures were consistent with a universe containing the predicted total baryon density, meaning the missing baryons were out there, in the intergalactic medium, just too diffuse to have been caught before. Half of all ordinary matter in the universe spent decades hiding in plain sight, stretched across the cosmic web in a form just barely detectable enough to finally be found. Sit with the implication of that for a moment. Not the dark matter we cannot identify, not the dark energy we cannot fully characterize. The ordinary matter, hydrogen and helium, the simplest atoms, the ones whose physics has been understood since the early 20th century, managed to conceal half its total inventory from human science for the better part of a century. The matter we understand the best, described by equations we have trusted for generations, was only half accounted for until very recently. So if 50% of ordinary matter, the 5% slice of the universe that represents everything we have ever directly studied, spent decades missing from our inventory, what does that say about our understanding of the remaining 95% dark matter has been inferred from gravitational effects for nearly a century and still has no confirmed particle identity? Dark energy was discovered by accident in 1998, and its fundamental nature remains an open question. And now we know that even the component of the universe we consider fully understood was only half visible to us until 2017. The honest answer to how well we understand the universe is we understand the parts we can see, some of the time with instruments sensitive enough to detect them. The parts that are slightly too hot, or slightly too cold, or slightly too diffuse, or interacting through forces we have not yet measured. Those parts have a history of staying hidden far longer than anyone expects. We spent 80 years finding half of the matter we theoretically understand completely. Dark matter and dark energy have presumably been observing this process with something approaching relief thinking. Quietly, that if we needed 80 years to locate ordinary baryons hiding in plain sight along filaments we already knew existed, the timeline for finding them is looking quite comfortable. The universe keeps score in a way that does not favor our confidence. Every time science declares a reasonably complete picture of what exists, something turns up missing. First, it was the rotation curves that would not behave. Then it was the acceleration no one predicted. Then it was half the ordinary matter unaccounted for across 8 decades of searching. Each gap closed by a discovery that revealed an even larger gap beneath it. We have now seen the universe's emptiness from multiple angles. We have measured it between stars, between galaxies, across the cosmic voids, and written into the structure of the web itself. We have watched dark energy drive that emptiness wider every second. We have found that even the matter we thought we knew was only partially visible to us. The picture is not getting simpler as the data improves. It is getting more complete in some places and more uncertain in others. Simultaneously, we have seen the universe empty. We have seen it expand. Now it is time to look directly at the endpoint, at where the universe is heading across billions and trillions of years, and what is waiting there. The Big Freeze. That is the name physicists give to the most likely ending of the universe. Assuming dark energy behaves as a cosmological constant, fixed, unchanging, exactly as the current standard model describes it. The scenario unfolds across a timeline so vast that every number previously discussed in this story becomes a rounding error by comparison. Stars burn out first. The most massive ones go within millions of years, exploding as supernovae and leaving behind neutron stars or black holes. Smaller stars, like our Sun, last billions of years before expanding into red giants and cooling into white dwarfs. The smallest stars of all red dwarfs, the most numerous type in the universe, burn so slowly and so efficiently that some will persist for 10 trillion years. 10 trillion years. That is roughly 700 times the current age of the universe, but even they run out eventually. Star formation slows, then stops, as gas reservoirs are consumed and not replenished. The last stars flicker out. The universe enters darkness. What remains after the last star dies is a population of stellar remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning down, black holes sitting silent in the dark. Over timescales, measured in numbers that require scientific notation to write, even these remnants change. White dwarfs cool to temperatures indistinguishable from the surrounding space. Orbits decay. Galaxies, no longer lit by stars, gradually lose their structure as gravitational interactions eject objects outward and others spiral into the central black holes. Then the black holes themselves begin to die. Stephen Hawking's theoretical work in 1974 demonstrated that black holes are not perfectly black quantum mechanical effects at the event horizon cause them to slowly radiate energy, losing mass at a rate so glacially slow that a stellar mass black hole takes approximately 10 to the power of 67 years to evaporate completely. The supermassive black holes at the centers of galaxies, billions of times more massive, take correspondingly longer, up to 10 to the power of 100 years, a number written as a 1 followed by 100 zeros. After that, nothing structured remains. The universe contains only isolated subatomic particles, electrons, positrons, photons, neutrinos separated by distances so enormous that interactions between them become vanishingly rare, drifting through a space expanding toward absolute zero. No gradients, no energy differentials, no possibility of work being done. Thermodynamic equilibrium at the bottom of everything. That is the Big Freeze. Cold, dark, quiet, and final. Approximately 10 to the power of 100 years from now, if dark energy holds constant, the second scenario is faster, much faster, and considerably more violent. If dark energy is not a constant, but instead belongs to a category called phantom energy, a form whose density increases over time rather than remaining fixed, then the repulsive force driving cosmic expansion does not merely maintain its current strength. It grows, slowly at first, imperceptibly, but without limit. As it strengthens, the scale at which it overcomes gravity shrinks. Galaxy clusters, currently held together against the expansion by their mutual gravitational attraction, begin to be pulled apart. Then individual galaxies lose their cohesion. Then solar systems, the force that is currently only strong enough to separate galaxy clusters, given enough time and enough growth, eventually overcomes the gravity holding stars in orbits, then the gravity holding planets together, then the electromagnetic forces holding molecules together, then the nuclear forces holding atomic nuclei together. Space itself tears apart at every scale simultaneously, down to the quantum level. This is the Big Rip. Cosmological models placing it approximately 20 billion years in the future. If phantom energy is the correct description of dark energy's behavior, 20 billion years sounds distant, and it is distant. Longer than the current age of the universe, but measured against the 10 to the power of 100-year timeline of the Big Freeze, it is effectively immediate. The universe ends not with a long slow cooling, but with a sudden, total as catastrophic shredding of everything that exists, including the fabric of space-time itself. The third scenario, the Big Crunch, or its cyclical variant, the Big Bounce, sits at the opposite end of the spectrum. If dark energy is not constant and not strengthening, but instead weakening over time, then gravity eventually reasserts dominance over the expansion. The universe's growth slows, stops, reverses. Everything that has been expanding outward for billions of years begins falling back inward, accelerating as the distances shrink and gravity strengthens. Galaxy clusters converge, galaxies merge, temperatures rise. Eventually, all matter collapses back toward a single point, recreating the conditions of the Big Bang, in reverse, a Big Crunch. Some theoretical frameworks propose that this collapse could itself trigger a new expansion, a Big Bounce, cycling the universe through repeated expansions and contractions indefinitely. The Big Crunch is currently the least favored of the three scenarios by observational data, but it has not been ruled out. Dark energy's behavior over cosmic time remains insufficiently measured to eliminate any ending entirely. The 2024 DESI data release added a new layer of uncertainty to all three scenarios. The survey's results hinted that dark energy may not be constant, its effective strength showing possible variation across cosmic time in ways that the cosmological constant cannot accommodate. If confirmed by future surveys, this would increase the probability of either the Big Rip or some hybrid scenario combining features of multiple endings. The Standard Model's confidence in the Big Freeze as the default outcome rests on dark energy being exactly constant. Crack that assumption, and the range of possible futures widens considerably toward the more violent end of the spectrum. Take a moment to think about which of these three endings sits most uncomfortably with you. The Big Freeze, a universe that simply runs down over an incomprehensible span of time, growing darker and colder until nothing can happen anymore. The Big Rip, everything torn apart in a cosmic instant. 20 billion years from now, with no remnants and no space left to contain them. Or the Big Crunch, a collapse back into the conditions that started everything, possibly to begin again. Possibly not. Each answer reveals something different about what kind of ending feels like a genuine ending to a human mind. Good news. In the loosest possible sense, even the most aggressive timeline puts the universe's end at least 20 billion years away. Bad news. In the most immediate possible sense, the sun will exhaust its hydrogen fuel and expand into a red giant that engulfs the Earth in approximately 5 billion years. Whatever ending the universe is building toward, it is not actually our problem. Our problem is considerably more local and considerably more near-term. But before the universe reaches any of those endings, before the last star dies or the last atom tears apart, there is an intermediate phase that almost no one discusses. A deepening darkness that has already begun, that will last for hundreds of trillions of years, and that we are, right now, in the early stages of entering. We are living in the stellar era. That is the technical name for the current epoch of cosmic history. the period defined by the existence of stars, running from approximately 100 million years after the Big Bang to approximately 100 trillion years after it. Stars are the universe's engines. They forge heavy elements in their cores, generate the energy that warms planets, produce the light that makes galaxies visible across billions of light years. The stellar era is the universe at its most active, most luminous, most complex. It is the only era in which life, as we understand it, is possible. We are in it, and the peak has already passed. Approximately 10 billion years ago, the universe was forming stars at a rate 10 to 30 times higher than it is today. Gas was abundant, galaxy collisions were frequent, and the conditions for triggering star formation, dense clouds of cold gas collapsing under gravity, existed across the cosmos at a scale never since repeated. That period, roughly between 8 and 11 billion years after the Big Bang, represents what cosmologists call cosmic noon, the universe's most productive era of stellar birth, the moment when the cosmic web was most actively converting raw material into stars at the highest rate it has ever achieved. Since then, the rate has been falling. Continuously, measurably, irreversibly. The universe's gas reservoirs are being consumed, locked up inside stars, ejected by supernovae into the intergalactic medium in forms too diffuse and too hot to easily collapse into new stars, or simply dispersed by the ongoing expansion of space. The rate of new star formation today is a fraction of what it was at cosmic noon, and all current evidence suggests it will continue declining without reversal. There is no mechanism in known physics that would cause it to rise again. We did not arrive at the party early. We arrived after the peak, during the long, slow wind down. The universe, at the moment of our existence, is already past its most creative phase. Every year that passes, the universe forms fewer new stars than the year before. Not dramatically fewer. The decline is gradual on human timescales, invisible in any single lifetime or century, but measurably, statistically, definitively fewer. The engines are running down. This has a name beyond cosmology's clinical language. The universe is aging, and the stellar era, for all its apparent richness when viewed from inside a bright solar system on a warm planet, is already in its afternoon. What follows is darkness of a kind that makes cosmic voids seem warm and familiar by comparison. After the last stars exhaust their fuel after the final red dwarf, somewhere around 100 trillion years from now, burns its last hydrogen and cools toward invisibility. The universe enters what physicists call the degenerate era. The name is precise. What remains is degenerate matter white dwarfs slowly radiating their residual heat into an expanding void, cooling over timescales that dwarf the entire stellar era. Neutron stars, the collapsed cores of massive stars, spinning down across billions of years. Brown dwarfs objects that never accumulated enough mass to ignite nuclear fusion, drifting dark and cold through a universe that no longer produces light anywhere. No new stars form in the degenerate era. No new energy is generated. No nuclear fires burn anywhere in the cosmos. The universe contains mass, and it contains gravity, and it contains the residual heat of processes that ended an unimaginably long time ago. But it produces nothing new. It is a universe living entirely off its past, radiating the last of what the stellar era left behind, growing colder and darker with every passing trillion years. That era lasts, by current estimates, until approximately 10 to the power of 37 years from now, at which point even the protons making up ordinary matter may have decayed if certain grand unified theories are correct, dissolving the last solid remnants of the stellar era into their fundamental constituents. Then comes the black hole era. Black holes, which formed throughout the stellar era as the collapsed remnants of massive stars and the gravitational sinks at the centers of galaxies, become the dominant remaining structures in the universe. Everything else has either been absorbed, ejected, or decayed. Black holes do not radiate light in the classical sense, but they do evaporate slowly through the quantum mechanical process Hawking described in 1974, releasing thermal radiation at a rate inversely proportional to their mass. A stellar mass black hole, a few times the mass of our Sun, evaporates over approximately 10 to the power of 67 years. A supermassive black hole, a billion solar masses, takes closer to 10 to the power of 100 years. The black hole era spans this entire range, a period of darkness so long that the numbers involved are genuinely beyond human imaginative capacity, during which the universe's only activity is the imperceptibly slow evaporation of black holes into thermal radiation, one quantum at a time. When the last black hole evaporates, the degenerate and black hole eras end together. What remains is the endpoint of the Big Freeze, a universe of maximum entropy, maximum emptiness, and minimum temperature, containing only isolated particles separated by distances so vast that meaningful interaction between them essentially ceases. Think about where we sit on this timeline. The universe is 13.8 billion years old. The stellar era runs to 100 trillion years. We are not even 1/10 of 1% of the way through the era of stars. In terms of cosmic history, human civilization appeared approximately 4 seconds into a year-long film, and yet the peak, the moment of maximum star formation, maximum light, maximum creative output, is already behind us. We arrived during the decline and called it the Golden Age because we have nothing to compare it to. There is something both humbling and quietly clarifying about that. We worry, reasonably and urgently, about climate change and energy supplies and the long-term sustainability of civilization on one planet. These are real problems deserving serious attention. But set against the background of what is coming, a universe whose entire fuel supply is locked in stars that are forming at a declining rate, with no refueling possible, heading toward a darkness that will last 100 trillion years before even beginning to approach an end. Our local energy concerns have a certain perspective-shifting quality. The universe is not running low on energy in some recoverable sense. It is running down in a direction that physics does not reverse. Emptiness is not only the feature of space, it is the direction of time, and that raises the deepest question this story has been building toward. If emptiness is both the condition that made us possible and the direction everything is heading, is it the reason we exist, or the reason we will one day be gone? The universe contains approximately 2 trillion galaxies. Each galaxy holds, on average, hundreds of billions of stars. A significant fraction of those stars have planets. A fraction of those planets sit in the habitable zones of their stars, not too hot, not too cold, with conditions that could, in principle, support liquid water and the chemistry of life. When you multiply those fractions across 2 trillion galaxies, the resulting number of potentially life-bearing worlds is so large that the intuitive conclusion feels almost unavoidable. We cannot be alone. The probability of Earth being the only place in the observable universe where biology emerged and complexity developed seems, by the raw arithmetic, vanishingly small. Enrico Fermi sat down for lunch with colleagues at Los Alamos in 1950 and asked a question that has not been answered since. If the universe is as vast and old as it appears, and if the conditions for life are as common as the numbers suggest, then where is everybody? The Milky Way is old enough that a civilization arising even a few 100 million years before us, a fraction of the galaxy's age, would have had time, at even modest interstellar travel speeds, to colonize the entire galaxy many times over. The galaxy is 13 billion years old. Crossing it end to end at 1% of the speed of light would take 10 million years. A civilization with that capability arising 200 million years before, us could have visited every star in the Milky Way and returned to write a report about it, with time left over. And yet, there is no evidence they did. No artifacts, no signals, no ruins, no modifications to stellar environments detectable from Earth. Nothing. The search for extraterrestrial intelligence, SETI, has been listening systematically since 1960. More than 60 years of scanning the sky across radio frequencies, optical wavelengths, and increasingly broad spectral ranges with instruments of growing sensitivity pointed at thousands of target stars and regions. The search has produced one anomalous signal, the WOW signal detected in 1977, which lasted 72 seconds, was never repeated, and was never explained. Everything else has been silence, clean, consistent, unbroken silence across 6 decades of dedicated listening. The silence has a name in the literature, the Fermi paradox. And its most unsettling proposed resolution belongs to economist Robin Hanson, who published a paper in 1998 introducing the concept of the Great Filter. The Great Filter is simple in structure and devastating in implication. Somewhere along the path from simple chemistry to a civilization capable of leaving detectable signatures across interstellar distances, there is a step or a series of steps that almost nothing survives. A filter so effective that of all the places where conditions for life exist, nearly all produce nothing that persists long enough or scales up far enough to be observable from another star system. The filter explains the silence. The question is not whether the filter exists. The silence itself is evidence that something is preventing the galaxy from filling up with detectable civilizations. The question is where the filter sits relative to us. If the filter is behind us, if the hard step was something in our past, like the origin of life itself, or the emergence of eukaryotic cells, or the development of sexual reproduction, or the specific evolutionary path leading to technological intelligence, then we may have already crossed it. We may be among the rare outcomes that made it through. The silence is then explained by how improbable our existence was, not by how improbable our future is. That interpretation is uncomfortable, but survivable. If the filter is ahead of us, if the hard step is something civilizations encounter after reaching our current stage, something that terminates them before they can spread or signal, then the silence carries a different weight entirely. Every candidate for what that forward filter might be is, by definition, something we have not yet encountered and may not recognize when we do. Nuclear self-destruction, biological catastrophe, the thermodynamic ceiling of a civilization's energy growth, some attractor state that technological development reliably produces, the details of which we cannot currently imagine. If the filter lies ahead, the silence of the universe is not just an interesting puzzle. It is a warning about where the path leads. The biological emptiness of the universe may not be random. It may reflect a law physical, chemical, or biological that we have not yet understood, operating consistently enough across enough worlds to produce the silence we observe. A universe that has had 13.8 billion years to generate detectable complexity, and that has so far produced at most one confirmed example of it, is a universe that is either extraordinarily stingy with life or extraordinarily efficient at ending it before it becomes visible. The James Webb Space Telescope has opened a new front in the search. Its spectroscopic capabilities allow, for the first time, the atmospheric analysis of exoplanets in sufficient detail to search for biosignatures, chemical signatures like oxygen, methane, and nitrous oxide in combinations that are difficult to produce without biology. As of 2025, no confirmed biosignature has been detected in any exoplanet atmosphere. The search is ongoing. The sample size is still small, and absence of evidence is not evidence of absence. but the silence is extending into a new domain. Pause for a moment and consider which answer you find more disturbing. If the great filter is behind us, we are a cosmic rarity, alone in an observable universe that produced complexity almost nowhere else, surrounded by 2 trillion galaxies, containing quintillions of worlds where nothing like us ever appeared. If the filter is ahead, we are not rare at all. Life emerges regularly across the cosmos, but something waits further down the road that ends the story before it reaches the chapter where civilizations become visible to each other. One interpretation makes the universe feel empty. The other makes it feel like a warning. We built the largest radio telescopes ever constructed, launched observatories into space, beamed signals outward, and listened for 60 years across every frequency we could manage. The universe has not replied, not confirmed, not acknowledged the effort in any verifiable way. Perhaps it is not hiding. Perhaps it is simply practicing cosmic scale non-response, the kind of silence that is not absence of signal, but absence of anyone left to send one. Either way, the result is the same. 2 trillion galaxies, trillions of potentially habitable worlds, 60+ years of listening. One species, one confirmed example of complexity, one voice, speaking into the dark without an answer. The universe is empty of matter, empty of signals, and growing emptier with time. But there is one final perspective, one that flips the entire picture you thought you understood. If the universe had not expanded, you would not be here to notice. A static universe, one that never grew, never diluted its initial energy, never allowed temperatures to drop from the billions of degrees of the early cosmos, would have remained a dense, hot plasma of fundamental particles forever. Temperatures in the early universe were too high for atoms to form, let alone molecules. Complex chemistry requires temperatures at which electrons can bind to nuclei and stay there, at which covalent bonds can hold without being instantly broken by thermal collisions. That chemistry became possible only because the universe expanded and cooled over hundreds of millions of years. The emptiness is not incidental to the existence of chemistry. It is the prerequisite. Without expansion, without the growing distances that allow temperatures to fall, there are no molecules. Without molecules, no organic compounds. Without organic compounds, no biology of any kind, anywhere. Remove dark matter from the equation, and the problem compounds immediately. Without dark matter, providing gravitational scaffolding in the early universe, without those invisible halos and filaments seeding the density contrasts that allowed gas to collapse, ordinary matter disperses too uniformly for stars to form on any reasonable timescale. The structures that concentrate matter into stellar densities depend critically on dark matter collapsing first and pulling baryonic matter in behind it. A universe with only ordinary matter and no dark matter is a universe where the gas drifts evenly through expanding space, never achieving the local density required to ignite nuclear fusion. No stars means no stellar nucleosynthesis, no carbon, no oxygen, no silicon, no iron, none of the elements life requires beyond the primordial hydrogen and helium produced in the Big Bang. No stars also means no planetary systems, no solid surfaces, no sheltered chemical environments where complexity can accumulate over billions of years undisturbed. The emptiness goes deeper still. If the universe were significantly denser than it is if the voids were smaller, the filaments closer together, the overall matter density substantially higher, the radiation environment would be far more intense. High-energy photons and cosmic rays would constantly disrupt the fragile molecular bonds that complex chemistry depends on. DNA proteins, lipid membranes, structures that require billions of years of stable chemistry to produce and maintain would be shredded faster than they could form. The precise level of emptiness the universe exhibits is not merely compatible with life. It appears to be within the narrow range of densities where structures complex enough to be called alive can survive long enough to matter. This is the territory where physicists and philosophers invoke the anthropic principle, the observation that the universe's properties must be compatible with the existence of observers, because if they were not, no observer would be present to notice the universe's properties. In its weak form, the anthropic principle is simply a selection effect. We find ourselves in a universe hospitable to our existence because we could not find ourselves in one that is not. The emptiness of the universe, the expansion rate, the ratio of matter to dark energy, all of these sit, not coincidentally, within the range of values that permit complex structure to exist for billions of years. We observe a universe with these properties because universes with significantly different properties produce no one to do the observing. Emptiness is not the universe's flaw. It is not the absence of something that should be there. It is the operating condition of everything that is there, written into the physical constants, maintained by the expansion, enforced by the geometry of space itself. The loneliness of the night sky is not a sign that the cosmos failed to fill itself. It is the signature of conditions precisely calibrated, by physics, or by selection, or by both, for the existence of anything capable of looking up. And then comes the part that sits uncomfortably alongside all of that. The same dark energy that drove the expansion which made chemistry possible is still driving expansion now, and will continue to do so indefinitely. The cooling that allowed atoms to form continues, inexorably, toward temperatures where all chemical reactions cease. The growing distances that created the conditions for stars and planets are now growing faster, carrying those stars and planets away from each other, isolating gravitationally bound systems into islands of matter, separated by expanding voids no signal can cross. The mechanism that created the conditions for life is the same mechanism that is, on a longer timeline, dismantling those conditions, driving the universe toward the cold, dark, isolated endpoint described in the previous two parts. The same force, the same physics, the same dark energy driving the same expansion. It created us, and it is ending us, not through any malice or design, but simply because it does not stop. Expansion does not pause once it has produced sufficient complexity. It continues past the point of complexity, past the point of habitability, past the point of any structure whatsoever, because that is what expansion does. Consider whether that changes how the emptiness feels. Not the terror of it, necessarily, but the meaning of it. The void is not the enemy of existence. It was the nursery. The darkness between galaxies is not where life was denied. It is the space that made the density contrasts sharp enough to produce stars, the temperature low enough for chemistry, the radiation environment calm enough for biology to persist. You exist because the universe is almost entirely empty. Your body, your thoughts, every atom in every cell of you required the specific depth of emptiness this universe exhibits to come together in the sequence that produced you. The universe created exactly the right amount of emptiness for us to appear, and then we appeared and spent considerable effort lamenting how empty it is. The irony operates at a scale that no comedy writer has the nerve to attempt. A cosmos with 13.8 billion years of careful physics-driven preparation, producing creatures whose first instinct upon surveying the result is to find it lonely. You now understand why the universe is empty. You now understand where that emptiness leads. But the real question, the one physics itself has not yet found the language to answer, is what lies beyond all of that. Everything in this story, every galaxy, every cosmic void, every measurement of dark matter and dark energy, every supernova used to discover accelerating expansion, every filament mapped by SDSS and DESI, every calculation about the Big Freeze and the Big Rip. Every number that broke your sense of scale across the previous 14 parts. All of it exists within a region of space called the observable universe, a sphere approximately 93 billion light-years in diameter, centered on Earth. Defined by a single constraint, it is the region from which light has had enough time, in 13.8 billion years of cosmic history, to travel and reach us. That sphere is not the universe. It is the portion of the universe we can see. The portion bounded not by any physical wall or edge or ending of space, but by the speed of light and the age of time. Beyond the observable horizon, space continues. How far it continues, whether it ends somewhere, curves back on itself, or extends without limit, is a question current physics cannot answer with certainty. But what the leading theoretical frameworks suggest is not merely that the universe extends somewhat beyond what we can observe. They suggest it extends by a margin so enormous that the word enormous fails completely. Some inflationary models, the theoretical frameworks describing the rapid expansion of the universe in its first fraction of a second, predict that the total universe is larger than the observable universe by a factor of at least 10 to the power of 23. That is a 1 followed by 23 zeros. Our observable sphere, with its 2 trillion galaxies and its 93 billion light-year diameter, would be a grain of sand on a beach that stretches beyond any comparison language can carry. Other models yield larger numbers still. Some yield infinity. Not infinity as a poetic gesture toward vastness, but mathematical infinity, a universe that is literally without end in any direction, containing an uncountable number of regions identical in size to our entire observable sphere, each separated from the others by distances no signal can ever cross. Then comes the theory that makes even that picture seem conservative. Eternal inflation was developed through the work of Alan Guth, who first proposed cosmic inflation in 1980, and André Lien, whose refinements in the 1980s led to the chaotic and eternal inflation models still at the frontier of theoretical cosmology today. The core idea is this: the inflationary process that drove the universe's rapid early expansion did not stop everywhere at once. In most regions of space, inflation continues eternally, without end, generating new space faster than any physical process can catch up with it. Occasionally, in small regions, inflation ends. The energy driving it converts into matter and radiation, producing a hot, dense state that then evolves into a universe like ours, expanding, cooling, forming structures, developing stars and galaxies and, perhaps, observers. Each of those regions where inflation ends is a bubble. Our entire observable universe, all 93 billion light-years of it, all 2 trillion galaxies, all the dark matter and dark energy and cosmic voids and everything else, it is one bubble, one region where inflation happened to end. Outside it, inflation continues, generating more space and more bubbles in an eternal self-reproducing process that has no known termination. The number of bubbles is, in this framework, infinite. They are being produced constantly in a larger structure of perpetually inflating space, and they will never stop being produced. Each bubble may be different. The physical constants that govern our universe, the strength of gravity, the mass of electrons, the value of the cosmological constant, the specific properties of dark energy are thought to emerge from a process called vacuum decay during the end of inflation. Different bubbles may end inflation differently, producing universes with different constants, different particle physics, different forces. Some bubbles may produce conditions hospitable to stars and chemistry and life. Others may produce configurations where no complex structure can persist for more than moments. The multiverse, if eternal inflation is correct, is not a collection of universes all running on the same physics. It is an infinite landscape of physical possibility, of which our universe, with its specific and life-permitting constants, is one sample. No signal from any other bubble will ever reach us. The inflating space between bubbles expands faster than light can cross it, permanently. Any civilization in any other bubble, however advanced, however ancient, is causally disconnected from us in a way that makes the isolation between galaxies inside our observable universe look like neighbors sharing a wall. We cannot see other bubbles. We cannot detect them. We cannot interact with them. We cannot even determine from within our bubble whether the framework that predicts them is correct, because the evidence that would confirm or deny it lies permanently beyond any horizon we could ever reach. Now take everything this story has built: the emptiness between stars, the vast distances between galaxies, the cosmic voids spanning 330 million light years, the 97% of galaxies already beyond our event horizon, the trillion-year darkness of the degenerate era, the silence of the Fermi paradox, the cold arithmetic of the Big Freeze, and place all of it inside one bubble. One region where inflation ended, one grain of sand on an infinite beach of other bubbles, each containing their own version of everything, or nothing, or something our physics has no vocabulary to describe. The emptiness inside our bubble, the emptiness that felt terrifying at the start of this story, the 99.9999% vacuum of the Milky Way, the 330 million light-year voids, the accelerating expansion carrying galaxies beyond our reach forever. That emptiness is not the scary part anymore. It is the interior detail of a single bubble in an infinite foam of space that never stops inflating, that has no center and no edge and no observable boundary. That contains more unobservable reality than our entire cosmic history has equipped us to contemplate. The question that remains, the one that cannot be answered, and perhaps never will be, is not why our universe is empty. We have traced that answer through 14 parts. The emptiness is the condition of our existence, the inevitable geometry of gravity acting on nearly uniform matter over billions of years, the prerequisite for chemistry and stars and life. The question that remains is what the distance outside our bubble actually is, not the distance measured in light years, because light years are a unit defined by the speed of light in a universe with our physics. Outside the bubble, in the eternally inflating space between regions where inflation has ended, the concept of distance as we understand it may not apply in the same way. The physical laws that define measurement, that define what a meter is, what a second is, what it means for two things to be separated by a quantity we could express as a number, those laws exist inside our bubble. Outside it, in the inflating space between bubbles, our mathematical tools arrive at the boundary and stop working. The emptiness inside our universe has a size 93 billion light-years across. Measurable, describable. The emptiness outside it, the inflating space between our bubble and the next, between our bubble and the infinite others, has no size our physics can assign. It is not large in the way the Bode's void is large. It is not vast in the way the distance to Andromeda is vast. It is outside the category of things our units of measurement were built to describe, because our units of measurement were built from the physics of this bubble. And this bubble ends. Step outside on a clear night, tilt your head back, look up. What you see is a window, a small circular window cut by the physics of light and time into an otherwise opaque boundary. Through it, you can see stars, a few thousand of them, the nearest neighbors in a galaxy of 400 billion. Itself, one of 2 trillion galaxies in a sphere of space 93 billion light-years across. That sphere sits inside a universe that may be 10 to the power of 23 times larger, or infinite, or both in ways that make the distinction meaningless. That universe is one bubble in an eternal inflation that has been generating bubbles since before our concepts of time began, and will continue generating them after every structure inside our bubble has dissolved into thermal equilibrium. you are not looking at the universe. You are looking through a keyhole at a single room in a building whose size has no number, in a city whose boundaries cannot be mapped, on a continent that has no edge, on a world our language does not have a name for. The night sky is not full. It never was. But the emptiness it shows you, the emptiness that felt terrifying at the beginning of this story, is the smallest version of empty there is. The real emptiness is outside, beyond the horizon, beyond the bubble, in the space between everything and everything else, where light does not travel, where time does not run the way it runs here, where whatever is happening has been happening forever and will continue happening after the last black hole in our universe evaporates and the last particle drifts alone in the cold. We looked up and thought we were seeing the universe. We were seeing the view from inside one brief, improbable, luminous bubble asking what lies beyond it, with minds that grew from the bubble's matter, using language the bubble's physics made possible, staring outward at a darkness that does not end and does not answer. That is where the story stops. Not because it ends, because we run out of window,